Hi, my name is Deven Biehler. I worked under Dr. Manoj Karki this summer at the CPAS laboratory. I worked on improving the autonomy of an orchard path planning robot and all the safety features that went into that. My motivation for doing this project was the rapid decline of available farmers. As the population of people rise, there becomes a need for efficient and sustainable farming. The purpose of this specific research was that it addresses the gap in fully autonomous orchard navigating robots. The purpose of creating a robot with a fully autonomous pathing and mapping is that it allows much more capabilities on top of this base. For instance, in this picture we have an autonomous arm that can be used for harvesting fruit, pruning flowers, spraying fertilizer, etc. Combining pathing with actual utility in the field creates a system that is great at tending to an entire orchard. This entire system was created to accurately map and traverse the orchard. This is all the technology that I installed or was already pre-installed in the robot's frame. The LiDAR and the RealSense camera help with mapping, while the IMU, GPS, and odometer help with the location of the robot. The ClearPath Warthog was chosen as our frame as it is a commercial use base that is very robust, can hold a heavy payload, and robot arms or any other sensing technology. Here's where I installed the LiDAR. The LiDAR sends out a 2D plane of light that bounces off of nearby objects and then re-enters the LiDAR, giving the depth values for each point. This is similar to the way that radar is able to find nearby objects with sound. This is the optimal placement to view all of the tree trunks without seeing leaves in the trees and without seeing the grass on the ground. Once the LiDAR data comes back to the sensor, it returns depth values. This depth data is then translated into point cloud information for easily processing. The point cloud is visualized here on the bottom to easily see what the robot is seeing. Each of these clusters of points is most likely a tree trunk or a pole or other farming equipment. This will all be sorted at a later time though, as we'll need to do some other pre-processing first. Here's where we apply a linear regression on the points within the red box. The data in the red box is relevant because it has a higher definition and is less likely to be noise from grass or tree foliage. The algorithm works well for predicting lanes, but it's not perfect. That's why I need to increase the accuracy by implementing this next technique. To predict a better line, we predict a line that's in line with the previously generated line. We're applying a weighted linear regression, giving high weights to the weights that are in line with the previously generated line. On top of this, the robot averages the line over the last few seconds of predicted lines to cancel out any outliers that might throw the robot off course. The blue line is created afterwards as a result of the other two green lines, and it's just an average between those two. The robot strives to follow this as closely as possible. Here are all possible scenarios for the robot when traveling. The robot could be traveling towards the path line, and in this case, just continue forward. The robot could be traveling away from the path line, in this case, turn towards the path line. The robot could be already in line with the path line, and then in that case, just continue with the path line. This ends up being a relatively simple algorithm, but very robust. The bottom graph is an actual test that I did, where I manually drove the robot through using a controller, and then had the autonomous algorithm drive it as well. As you can see, the paths are relatively close, only a few centimeters at the widest distance. Here's an example of the autonomy in action. Below we can see a tool called RViz, which is able to see the live update of the path line. I have a RealSense camera attached to the front of the robot. With this alone, I can 3D map the entire orchard. The RealSense camera is basically a set of two cameras that take a picture of an object. With these two images, you can check the disparity between them and calculate a depth value. We can use this to create 3D images of anything we'd like. I used YOLO V8 in this project. YOLO V8 is an object detection algorithm which was already previously designed by machine learning engineers. A RealSense camera was attached to the side of the robot that gets a picture of the trunk and confirms where the LiDAR data thinks it is. The LiDAR data with the YOLO data can confirm the location of each tree trunks, giving an accurate and robust location of all of the tree trunks. We combine this with the orchard mapping to get a very nice and understandable view of the orchard. All three of these sensors were already installed in the Warhawk's frame. They were combined using an EKF filter or an extended Kalman filter. With this new autonomy, we needed new safety features. The LiDAR worked great for this. It's very robust and it's able to precisely tell the distance of any unprotected object in its way. Anytime I step in front of the sensor's range of about half a meter, the robot stops as quickly as possible. I had a great time this summer. I wanted to say thank you to everyone that made this possible, including Agaid, my mentor Chup Patel, and my PI Minash Karki.